Bismillahirrahmanirrahim. Dear friends, in this video, we will calculate wind pressures for this structure using ASCE 716 specifications. The structure is having monoslope roof. These are the dimensions of the structure and these are cardinal axes for our reference. But before proceeding to this example problem, I will discuss something related to example 1 that we have covered in previous video. I have made two mistakes in that example. Let me explain. We combine external and internal wind pressures using this equation. We can see that there is a negative sign in between, which means that when we are considering positive GCPI, then equation look like this. And when we are considering negative GCPI, then equation look like this. What I did, I have shuffled both the cases. Let me show the correct pressures. For load case 1, when wind is blowing from west to east direction for case 1 with positive GCPI, this is the plan view of the structure. These are the windward and leeward pressures. Here we can see that the internal pressure is now subtracted from the external wind pressure. Why? Because we are considering the positive GCPI. Similarly, the pressures for the side walls and when we are seeing the section view, so these are the pressures on the windward and leeward walls, and these are the roof pressures from 0 to H region and for H to 2H region. Now when we see the isometric view, the pressure are look like this. The roof pressure shown in blue color is actually for the region 0 to H, and in green color from H2 to H. It is running uniformly on the entire length of 60 feet. The second mistake I have done is shown in the region wise in the 60 feet direction, which is wrong. Likewise, all the pressures for all the cases are shown. For load case 9, when wind is blowing from south to north, for the case 1 with positive GCPI, these are the windward wall and leeward wall pressures and these are the side wall pressures. When we cut a section AA, then we can see that these are the side wall pressures, and when we cut the section B, then region wise from 0 to H is this pressure, from H to 2H is this, and for greater than 2H is this pressure. Now in section AA, what these pressure look like? This pressure is look like this. It is gradually decreasing. So I have not shown all these three in the section AA, rather I have written over all these three values. Likewise, all the load cases. So these were the mistakes that I have made while explaining example problem 1. So now let's get back to our example problem 2 and see how to calculate wind pressures on a monoslope roof building.
Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends. And let's learn structural engineering together. One more thing, we have already started design courses related to reinforced concrete structures and steel structures along with the steel connection design. If you did not watch those videos, then please go and watch those. Links of these videos I am sharing in the description below. So let's get started.
The design data of example problem 2 is shown, where wind velocity is 150 mph, building exposure is B. It's considered as rigid structure having gust effect factor as 0.85. Building category is 2 and is located on homogeneous topography. The dimensions of the buildings are shown. Proceed for the solution. First step is to calculate the velocity pressure using this particular equation. We require these factors, so we will pick from the tables For the KZT, we are using value 1. For KD factor, we are using 0.85 because bend wind force resisting system. For KE factor, we are conservatively using as 1. We will calculate wind pressures at these levels. Z is equals to 20, Z is equals to 25 and Z is equals to 30. Z is equals to 25 is mean roof height. So we will use this table to find out KZ factor at 15 feet, because from 0 to 15 feet the wind pressure is uniform and then it will change as per height. So KZ value against each Z value is shown. Now after plugging all the values in the above equation, we get QZ as this, and here velocity pressure at mean roof height, which is QH, is 32.31 highlighted in red. Now step 2 is to find out the internal pressure coefficient, as we are having no openings in the building, so A0 is 0. So building is considered as enclosed. Using this particular table, under the enclosed building classification, internal pressure coefficient is plus minus 0.18. Now step 3 is to find out the external pressure coefficient. Note that L is equals to length parallel to wind direction considered and B is length parallel to wind direction considered. For walls, length over breadth ratio are shown for each directions of wind. We are using this particular table to find out the CP value for walls. As we can see that for windward and side walls, CP value is not dependent upon length over breadth ratio, while for leeward walls it is dependent upon the length over breadth ratio. For wind west to east or east to west, length over breadth ratio is 0.571, which is less than 1, which is in between 0 and 1, so CP is minus 0.5. But for north to south or south to north direction, it is 1.75, which is in between 1 and 2, which is not in the table, so we have to interpolate it. So let's do the interpolation. We need to interpolate CP value against length over breadth ratio 1.75, which is in between 1 and 2. So x1 is 1, x2 is 2 and x is 1.75, at which we need to find out CP value, and y1 is minus 0.5, y2 is minus 0.3, so it's minus 0.35. So by interpolation, for L over B is 1.75, we get CP as minus 0.35. For wind west to east, H over L ratio is 0.625 and theta is 14.03. It's calculated by using simple trigonometry. Remember this particular table, last time we use only the lower portion of this table because our theta is less than 10 degrees. But now this time our theta is greater than 10 degrees, so we'll have to use the upper portion of the table. Wind direction normal to ridge for theta is greater than 10. Let me show you the ridge. In our structure, this particular line is considered as ridge and we are calculating the wind for west to east. So this means that wind is normal to ridge, means perpendicular to ridge. So there are the two cases here, windward and leeward. When wind is blowing west to east, so this roof is considered as windward, and when wind is blowing from east to west, then this roof is considered as leeward. So for west to east, roof is acting as windward. There are two values for CP, means two cases has to be determined. We can see that for each H over L ratio for against each theta, we are having the two values of CP. So there are two cases. First we will find out CP value for case 1. We can see that our H over L value is 0.625, which is not in the table, and theta is 14.03, which is not in the table as well. So we require double interpolation here. First, let's figure out between which values we will have to do the interpolation. So first we'll do the interpolation for CP value against H over L. So first we will look for roof angle 10 degrees. For H over L 0.5, roof angle 10, CP value is minus 0.9. For H over L 1, roof angle 10 degrees, it's 1.3. But here it is superscript B written, where in the notes we will find out that this value can be reduced against the applicable area. So using this particular table, we can actually find out the reduction factor for this particular value of CP. So we are finding out the wind pressure for roof. So we are having the dimensions of the building as 70 foot and 40 foot. Although it's inclined, but on a roughly basis, it's 70. It's a projected planned dimensions. So 40 foot and 70 foot is okay. So 40 by 70 foot is 2800 foot square, which is greater than 1000 foot square. So the reduction factor can be used as 0.8. So 0.8 times of 1.3 is 1.04. So here we can write it as 1.04. And we will look now for theta 15 degrees. 0.5 against H over L 0.5. In theta 15 degree, we can see that it is minus 0.7, and for 1 it's minus 1. Let's do the interpolation one by one. For H over L 0.5 and 1, and our desired value is 0.625, it's minus 0.9, minus 1.04, so it's minus. Now for theta 15 degrees, it's minus 0.775. So now for theta 10 degrees, CP value is minus 0.935. For theta 15 degrees, CP value is minus 0.775. And for our desired theta 14.03, let's do the interpolation. 10, 15, 14.03, minus 0.935, minus 0.775. So our desired value is minus 0.806. So after interpolation, we will get these values. Now for case 2, we can see that all the values are same, which is minus 0.18. So we do not require any interpolation here. Now for the wind direction east to west, H over L value and theta remain same, but now roof is acting as levered roof. We can see that in the levered section there is only one CP value. So in both the cases we'll use this value, but the interpolation required here. So in the similar fashion, after interpolation we will get these values. Now for wind north to south, H over L value is 0.354. Now this time wind is parallel to ridge, so we are looking into the lower portion of the table now. Since H over L value is less than 0.5, so there are the 4 regions similar as example 1. The values are shown for both the cases. Now step 4 is to find out the design wind pressure using this particular equation. So for windward wall, QZ varies with Z, and QH is equals to QZ at Z is equals to H, which means mean roof height at 25 feet. So at Z is equals to 15 feet, QZ is this. At Z is equals to 20 feet, QZ is this. At Z is equals to 25 feet, which is mean roof height, QZ is this, which is equal to QH. And Z is equals to 30 feet, QZ is this. So P positive GCPI means pressure with considering the positive GCPI and pressure considering the negative GCPI. So these values are shown here. Now for side walls, QH is used in both the terms. for leeward wall, for wind east to west or west to east, and for north to south or south to north. For roof, when wind is blowing from west to east, for case 1 the pressure is shown, for case 2 the pressure is shown, and for wind east to west the pressure is shown. For both the cases, case 1 and case 2, pressure are same. For wind north to south or south to north, for case 1, for region 0 to H, for H to 2H, and for greater than 2H region, pressure are shown. For case 2, all the regions are having the same pressure. I have discussed this chart in the last video, so there should be 16 cases. So let's see one by one. For load case 1, when wind is blowing from west to east, for case 1 with the positive GCPI, this is the plan view, this is the windward wall, and its pressure is varying with Z, and it's the leeward wall pressure, these are the side wall pressures. When we cut a section AA, so we can see that the windward face are having 2 pressures, because from 0 to 15 feet the pressure is same, and above the pressure changes as Z. Now the roof is acting as windward roof here for this particular wind direction, so the pressure is shown, and in the isometric view the pressures look like this. For load case 2 with the negative GCPI, all the things are same except the positive sign in between, so the pressure value changes. Similarly, for load case 3, when wind is blowing from west to east, case 2 with the positive GCPI, and for load case 4 with the negative GCPI. Here we can see that on the roof it is positive pressure now, so it is acting towards the surface. In the isometric view we can see that. For load case 5, wind is blowing from east to west, so this one will become the windward side now, and this particular pressure is the average of the lower third pressures. Now this time roof is acting as a leeward roof, so leeward pressure is this, and we can see that in the isometric view the pressure look like this. Similarly, for load case 6 with the negative GCPI, this is also the average value. For load case 7 with the case 2 with the positive GCPI, for load case 8 with the negative GCPI, for load case 9, wind is blowing from south to north, for case 1 with the positive GCPI. Now this time windward wall is this is the leeward wall, and these are the side walls, so the pressures are shown. In the section view, now this side are now become the side walls. Now in the isometric view we can see that there are the 3 regions now, from 0 to H, H to 2H, and greater than 2H. So from windward side the pressure is greater and it is reducing as the distance from the windward side increases. Now in the section AA I have only mentioned a single UDL. 3 different pressures are written over here, which is linearly decreasing. Similarly, for the load case 10 with the negative GCPI. For load case 11, case 2 with the positive GCPI. Now this time there is no need for the region wise calculation because it's a case 2 having the uniform pressure inside the roof. For load case 12 with the negative GCPI, now this time the pressure is positive, so it's acting towards the surface. For load case 13, north to south, this time windward wall is this and leeward wall is this one, and these are the side walls and these are the roof pressures. Now the windward wall is opposite side, so the greater pressure is from the opposite side and it's reducing linearly as shown. Similarly for load case 14 with the negative GCPI and load case 15 case 2 with the positive GCPI having the uniform pressure, and load case 16 with the negative GCPI. So this ends of our example problem 2. I have taken the simple structure in this example so that I can explain the things more clearly. Later on we will add a video to our analysis and design playlist to show how to design and assign these loads in analysis softwares. Further, in the next videos of this playlist, we will see different structures for calculating wind load pressures. I hope that through this example, you people get better understanding of calculating wind loads using ASCE 7 specifications. If you liked our video, then please hit like and subscribe button and share as well with your friends. And you can comment below for your desired content or video. I will try to make that content for you. So this is up for today. See you in the next video.